Welcome to today's ArXiv CS Digest for February 27, 2026. We received 715 new computer science papers today across 59 subfields. Let's dive into the top picks. Up next, our first paper out of 5, The Sample Complexity of Online Reinforcement Learning, a Multimodal Perspective by Michael Muhlebach and Michael I. Jordan. Let's break down its key contributions. This framework addresses online reinforcement learning in general nonlinear, non-episodic settings. It accommodates diverse dynamical systems, from finite candidate models to Lipschitz continuous dynamics, providing a robust foundation. A novel online reinforcement learning algorithm is proposed for general nonlinear dynamical systems. It achieves specific policy regret bounds by effectively managing model complexity through discretization and packing numbers. The methodology includes an adaptation for systems with dynamics parameterized by compact, real-valued sets, like neural networks. This specialized approach achieves improved policy regret bounds, recovering results from linear systems. Up next, our second paper out of 5, Regularized Online RLHF with Generalized Bilinear Preferences by Younghyun Lee and Se-Young Yoon. Let's break down its key contributions. This paper adopts the Generalized Bilinear Preference Model, GBPM, to effectively capture potentially intransitive preferences. It utilizes low-rank, skew-symmetric matrices, providing a robust framework for modeling complex preference structures in online RLHF settings. The work investigates general preference learning with any strongly convex regularizer and regularization strength $1. This generalizes beyond prior work limited to specific regularizers, enhancing the model's flexibility and applicability across various scenarios. A central theoretical contribution is proving that the dual gap of the greedy policy is bounded by the square of the estimation error. This crucial insight, derived from strong convexity and GBPM skew symmetry, forms the analytical foundation for the proposed algorithms. This algorithm achieves polylogarithmic $e⁻mathcal O eta $free regret, specifically $mathcal O eta d⁻4 log t $2. It provides an efficient and practical approach for online RLHF, building upon the theoretical insights and the generalized preference model. This algorithm exploits the low-rank structure of preferences to achieve $mathrm, poly, d, $free regret $mathcal, o, /sqrt, eta rt, $. It is the first statistically efficient guarantee for online RLHF in high dimensions, offering significant performance improvements. Up next, our third paper out of 5, REPO, Robust Enhanced Policy Optimization as a General Framework for LLM Alignment by Xiaoyang Chao and Chao Yu. Let's break down its key contributions. REPO employs an expectation maximization procedure to infer the posterior correctness of each preference label. It then adaptively reweights data points in the training loss, effectively mitigating the impact of label noise and improving model alignment. REPO establishes a theoretical link between various preference losses and their probabilistic models, systematically transforming existing alignment algorithms into robust versions. This elevates REPO into a general framework for robust preference alignment. Up next, our fourth paper out of 5, Compositional Generalization Requires Linear, Orthogonal Representations in Vision Embedding Models by Arnaz Uslis and Sung-Jun Oh. Let's break down its key contributions. This contribution formalizes 3 essential desiderata: divisibility, transferability, stability, required for compositional generalization in neural networks. These principles establish the foundational requirements for robust generalization. Based on the formalized desiderata, the paper derives necessary geometric constraints for representations. These dictate that representations must linearly decompose into orthogonal per-concept components, crucial for generalization. This contribution further derives quantitative dimension bounds. These bounds link the number of composable concepts directly to the embedding geometry, providing a deeper understanding of representational capacity. The paper empirically evaluates these theoretical predictions across modern vision models like CLIP, SIGLIP, and DINO. This validates the proposed representational structure's correlation with compositional generalization. Up next, our fifth paper out of 5, Open Rubric System, Scaling Reinforcement Learning with Pairwise Adaptive Rubric by Ruiping Jia and Guanjuan Jiang. Let's break down its key contributions. OpenRS is a novel, plug-and-play LLM as a judge framework that operationalizes explicit, inspectable reasoning for reward generation. It addresses the limitations of scalar reward models by providing a structured, rubrics-based approach. PAMR introduces an explicit meta-rubric that dynamically instantiates adaptive rubrics by conditioning on semantic differences between candidate responses. It performs criterion-wise pairwise comparisons, aggregating preferences externally to improve discriminability in open-ended settings. PVRs are lightweight rubrics providing hard constraint guardrails and verifiable reward components for objective subtasks. They act as crucial checks against degenerate behaviors, ensuring robustness and incorporating ground truth or programmatic verifications when available. A two-level meta-rubric refinement pipeline ensures consistent yet editable principles. It combines automated evolutionary refinement for general principles with a human-in-the-loop procedure for domain-specific principles, enhancing adaptability and maintainability across various domains. The Open Rubric system is instantiated as a robust reward supervision mechanism for pairwise reinforcement learning training. This application demonstrates how explicit, inspectable rubrics can effectively guide and scale alignment in complex, open-ended tasks.